Now in this video, we're going to talk about simplifying radical expressions. We're going to continue our work, but this time we don't have perfect squares and perfect cubes in the way that we did in the previous video. There are some strategies to simplifying radical expressions. You're going to use a factor tree to find the prime factorization of the radicand. Now remember, the radicand is the number inside of the radical. So this first example, square root of 20, it says to make a factor tree for the 20, okay? Then it says use the index to determine how to group the factors. Again, remember from the last video. So when you have a radical root like this one where the index is not written in, it's understood that there's like a little invisible 2 there. It's like there's a little missing little 2 that's not written there, little 2, and that's your index in a square root. And we don't have such a thing as a 1 root, just in case you were wondering. So this says that if this is a little invisible 2 here, that when we do our factor tree for 20, we're going to group the factors in groups of 2. And then it says for each group, one factor leaves the radical and goes outside the radical. So each group of 2, so if you were looking for squares, the square root of a square is the single number, right? And then multiply the outside factors together and multiply the inside factors together. Okay, so let's just look at this first one. Okay, square root of 20. So factor tree for 20 is 2 times 10, right? And then 2 is prime. So 10 is 2 times 5. And so now we have all the factors of 20, right? So we have 2 2's and a 5. And we're trying to take the square root of that. And it says here, use the index. So the index is 2 to determine how to group the factors. So we're going to group the factors in groups of 2. So, and as you know, we have these 2 groups of 2 right here, these 2 2's together. So for each group of 2, one factor leaves the radical. So for 2, a group of 2 2's, which is square root of 4, right? 2 times 2 is 4. Square root of 2, the square root of 2 times 2 is 4. The square root of 4 is 2. So therefore, this group of 2 2's, one leaves the radical and goes outside. So we have 2 square root of 5. The 5 is a single. There's not 2 5's. So we can't take any factors outside of the radical. Okay? So again, 2 ways to think of this. You could think of square root of 20 as the square root of 2 times 2, which is 4, times the square root of 5. And you can think of the square root of 4, evaluate this because you know that that's a 2, just a single 2. That's 2 becomes the coefficient, goes in front of that radical 5. Okay, so that's one way of thinking of it. And the other way of thinking of it is this idea where we do the prime factorization of 20 and we look for groups of 2 of one factor. And since we have 2 2's, for each group of 2 2's, one goes outside the radical. So that becomes 1 2 outside the radical. And this extra little 5 stays inside the radical. Okay, so hopefully one of those 2 versions works with the way you think. Okay, square root of 72. So again, we're going to do a little factor tree. Again, index is 2. Numbers that go into 72, well, you know that 72 is an even number. So there's some rules here I gave you, divisibility rules. So in case you don't know what goes into numbers, there's some kind of neat rules. So for example, for 72, of course, if it's even, as you know, then we know 2 goes into 72. So it's 2 times 36 when you divide square root of 72, right? And so 2 times 36, and then 36 is a perfect square. You could stop right here. You could just say, oh, I recognize that square root of 36 as a perfect square. So I know that this number is just 6, and then I have that extra little square root of 2. So this would be 6 square root of 2, right? So that's one method. But the other method was, maybe you don't recognize 36 as this perfect square. So you're going to keep finding the prime factors. And so 2 goes into 36 18 times. And then 2 goes into 18 9 times. And then 9 is 3 times 3, right? So as we look at the ends of all these branches here, right, we're looking for groups of 2 things. So here's one group of 2 2's, and here's one group of 2 3s. Sorry, you can't read that. That's a 3. One group of 2 3s. And then this guy's by himself. So for this group of 2 2s, 1 goes outside the radical. 1, 2. For this group of 2 3s, 1 goes outside the radical. And you multiply those together to get the 6. And this extra 2 that was right here, that stays in the radical. That helps. Okay. Cube root. Okay, so now we're going to look for cube roots. Now we're looking for groups of 3. Groups of 3. Again, we're going to factor this. Factor tree. Even number. 2 times 81. I'm doing the division in my head, but you could use your calculator. Okay, and then 81. Well, I know that's 9 times 9. Right? Then 9. 3 times 3. 3 times 3. And another 9. 3 times 3. Okay, so here's what I've got. Let me line them up. I have 1, 2 from here, and I have 1, 2, 3, 4 3s, don't I? So there's my prime factorization. I'm trying to take the cube root of this, so I'm looking for groups of 3. So here's one group of 3 3s. That's the only group of 3 that I have. So one of these, the cube root, and this is 27. Can you recognize that? Cube root of 27, which is a perfect cube. For this group of 3, cube root of 27, 1 3 comes outside the square root. The radical, sorry, not the square root, the cube root. Cube root, so that came from here, right? And then these 2 get multiplied and stay in here, and that's 6. Cube root of 162 is 3. Cube root of 6. Don't forget this index, by the way. If you're typing this into a computer homework system and you don't put that little index in there, it will mark it wrong. So you want to make sure you do that. Okay, let's go to the next one. Now we have some variables here.